My name is Tara Schrader, and good afternoon. I will spend the next 45 minutes telling you how you can make electrical compliance easier. And a little bit of background about me. I have spent 16 years in the aerospace industry, started out as a systems engineer, and as a systems engineer, I did a lot of systems integration, as you might expect. I also did a lot of flight testing. I'm a pilot myself. And then I moved into programs, and in programs I was responsible for things like cost, schedule, and scope or performance, as you might imagine. And in both of those roles, systems engineering and programs, I spent a lot of time working certification and compliance. So working with authorities such as the FAA, EASA over in Europe, Transport Canada, ANAC down in Brazil, the JAA in Japan. So a lot of experience in this regulatory space, which has really spanned my career. And you'll see a lot of airplanes in these slides because I really like airplanes. But we could have just as easily had someone do this presentation about automobiles or industrial machinery. Because these ideas that I'll show you today and these analysis methods really apply to a whole host of industries and really to any complex equipment or machine that has electrical content. So you'll see a lot of planes, but the concepts are easily transferred. So having said that, let's look at an airplane. So this is a flight deck of a modern aircraft. You can see these kind of fancy flat panel displays. And modern aircraft have a lot of electrical systems that enable fancy capabilities. They have things like fly-by-wire. We also have things that you use when you fly probably every time. In-flight entertainment, the USB charger on the seat back. And so this electrification brings us a lot of nice benefits and a lot of capabilities. But there's a trade-off to that, right? We also have a lot of complexity. And that complexity is difficult to analyze, and it can be very difficult to show regulatory compliance with things that are very, very complex. And we know that it is getting more difficult, and the primary reason for that is complexity. So just to kind of drive that point home, I have some statistics here, and you can read them. 300 miles of cable length, that's a lot of miles. 100,000 wire segments, things like 15,000 pounds of weight, 40,000 connectors. We're talking about a lot of content. These numbers are for sort of air transport category aircraft, Part 25 aircraft, if that's kind of your thing. But we have very similar numbers for military aircraft, cargo aircraft, things like that. So we know that these are complex systems. And we can also see things like increased electrification. We can see the Airbus A330, the A380, the Boeing 787. We see that the power curves from these systems are really, really increasing fast. And if we look at electrical power as a proxy for electrification, you could also look at that as a proxy for complexity, we see that the data backs that up. We have some important things here. EWA's cost grows faster than the content. You know, for folks in the industry, they know that EWA's is electrical wiring interconnect system. But the cost is growing faster than the content. We see that in other disciplines also, and we see it here too. So we have a number of challenges in the industry. Like any industries, we need to be profitable. So we look at things like margin pressure. We look at things like COGS. You know, how do we drive down the cost of goods sold? Just-in-time deliveries. The company for which I worked, like many companies in the industry, followed lean electronics, and so you don't want inventory sitting on your shelves. People look at that as just cash sitting on your shelf. So we're really looking at doing things at the last minute possible. Of course, it has to be quality. It has to be delivered on time. And one of the big elements in that chain is regulatory compliance, because we know that if our aircraft don't comply with the regulations, we can't sell them and we can't fly them. So delivering aircraft to customers on time can get very difficult with very complex systems. I know this from experience. You are committed to your key program milestones long before you start the program, and certainly before you know what's going to bite you. You don't know where all the risks are because you find those out as you work them. But your milestones don't move, right? So there's a lot of pressure. We know that they carry a high degree of risk. There's a lot of risk around these milestones. On Thursday, Tony Nicoli will be giving a session on how we can help reduce that risk in many areas, compliance being one of them. But there is a lot of risk there, and we know that there's a lot of attention because we can see in this overall kind of very, very high level program time frame, we see that type certification and customer acceptance is kind of that final step before entry into service. And entry into service means that's where we get money. That's where we start kind of getting some money in for all of our NRE going out. So it's a big deal. And we've said before, it's difficult. A lot of these methods being employed today are very manual methods. And I have a couple points here. It's very onerous and expensive. These methods today are very disconnected. They're using a lot of different tools. There's a lot of copying and pasting, a lot of looking for data. And these methods were fine when electrical systems were far more simple. They get really difficult with complexity. And again, working programs before, I know that you budget to do this once. You don't budget, you don't have the hours to fund that effort multiple times iteratively throughout a program. You do it once, and so you wait until your designs are mature, and then you do your formal, what they call for-credit analysis, which is fine if you don't find any problems, but I've never seen a program like that. And so that means that your rework is coming at a very critical phase. We know that it's more expensive to correct design issues later on than it is at the beginning. So just a whole host of problems. And so we've spoken with a number of our customers about how do they perform their electrical compliance activities today. And here's some of the feedback we got. I never know if I'm analyzing current data. From very big major aircraft OEMs, we heard this over and over again. We spend weeks writing the report only to find the references are outdated. This is a very big problem. Sometimes we forget to analyze entire buses. When you have things like, essential and non-essential buses and then full redundancy with those buses, you'll have a standby or emergency battery backup bus. It is very expensive to catch that lack of analysis and peer review. And again, these are companies who've been in the industry for a long time and they know what they're doing, and still we have these very, very fundamental problems with this. And again, a lot of findings in peer review due to errors. It's an expensive time to find problems. So here's what we learned. Tools being used today are very disconnected. They're very manual. We heard a surprising number of companies using Fortran because their Fortran programs still work. But it's getting increasingly more difficult to put all of that, all of their models in their electrical system into Fortran. Of course, Excel is used, a number of homegrown tools, and at most companies it was a mashup of all of these things to kind of get to their compliance, their evidence of compliance. And of course, we need to do this for every configuration. So let's say that Delta Airlines and American Airlines both order a 737. Those will be different configurations. Maybe some are outfitted for ETOPS, so they can fly over the ocean. So maybe their sensor suite is a little bit different than non-ETOPS aircraft. So doing that for every configuration for the complexity, it's a big problem. So how do we fix it? We can use digitalization. We can use modern digital techniques to help us design a system and help us analyze a system in a way that makes compliance easier for us. And so I have a quote here from Kristen Baldwin from the DoD about how the United States Defense Department is moving toward digitalization because they recognize this as a solution to this complexity and a whole host of benefits that come with that. So what does digitalization mean? We hear that word a lot. You've probably heard it already a lot today at this conference. So I will show you what does that mean for an electrical system. So we have things like a digital product, digital production, digital performance. And what this means is we can design and develop our electrical system virtually. So you have already seen this in the mechanical space. You've seen full 3D models of probably entire aircraft or entire vehicle systems. And so we're already really used to this concept in mechanical. So one of the things that I used to do when I was in the industry, we would do things like a clash analysis, which is just what it sounds like. Are my two pieces going to clash, or is there going to be an interference? We can do tolerance stack-ups. We can say if all of my tolerances skew the same direction, will my equipment still fit in the aircraft? And so these are things that we already are familiar with and we already know about. We can use that 3D model to do things like thermal simulations and CFD flows for aerodynamics. But we can also do that for electrical. We can analyze our system, and we'll show you more about that. Moving a little bit further down the line, digital production. We can look at things like work instructions. We can automatically generate work instructions that will assemble the unit that you've designed. So that's a very nice thing. When I was in college, I used to write work instructions by hand. And it sounds easy. And I tell you, no one reads that sentence the same way. And it was it paid my rent. But it was a very manual process. On the sustaining side, we can do things like, automatically generate a troubleshooting document for my wiring system. So that's a very nice use of digitalization. And this kind of all comes together in a holistic digital twin. And again, this idea is that you design it virtually, you analyze it virtually, you can service it virtually. You get a lot of benefits by doing this before you build the physical parts. And this is what we call the model-based enterprise. So you'll see MBE or MBSE. You see these terms used a lot. For us, this is what we mean by this, model-based enterprise. And so it has some components. There's some pieces to this. We have data coherency. So suddenly we have all of our data in one place. All of the units are the same. We're not trying to kind of convert units in our heads or trying to take it into Excel or Fortran. All of our data is coherent and consistent. Built to integrate. I spoke a little bit about that virtual integration in the mechanical space. We can do this in the electrical space also. So if we're expecting, this pin is ground, let's make sure that we have ground connected there and not power. This is a very gross example, but we can do these virtual integrations. If you're expecting a 429 twisted shielded pair into two pins, let's make sure that the wire type actually matches that protocol. So these are very, very rough levels of checking and integration, but very powerful. And these are the errors that I've seen firsthand get through peer review and design stages and things like that. It's very nice to do this digitally. We can automate things. I mentioned some of that rule checking. We can automate that, and we can have the software do some of this rule checking for us. There's no reason why a person needs to go through and manually over and over again check these same basic design rules. We can let the software do that for us. And this is part of Capital. So we have a lot of pieces of Capital. This is not meant to be an overall explanation of everything that Capital can do, because you can see that it's very broad. But here we are talking about this design space. How do we design and verify the electrical system? And how do we do it in a way, kind of getting back to our main topic, how do we do it in a way that's easier? It makes it easier to generate those artifacts for compliance and makes it convincing so we can sell aircraft faster. So some of these things that a digital twin allows you to do, you can configuration control it. We know you're going to have a lot of variants, a lot of derivatives of your aircraft design. All of those are configuration controlled. Comply by construction. And let me give you an example of what that means. As you are designing the aircraft and designing that electrical system, you can create rules. So for example, you can say, don't mix power and data, because we know you're going to get some EMI artifacts from that. We can say, don't mix your primary and secondary signals in the same bundle, because that really violates the kind of the intent of your system redundancy. And that's going to be rework for you later on. So you can use these rules to design your system with compliance in mind from the very beginning, with the idea of let's do it right so we're preventing rework later on. And because it is all at a press, very literally at a press of a button, you can verify design compliance as you go. So you've probably heard about agile methodologies. The idea, a big principle behind agile is build a little, test a little. This allows you to do that. And you know, this very bottom point, check, analyze, verify during the design. This is really where a lot of the power comes from, because as you make design changes and you continue to mature your design, you can see incrementally what is the impact of those compliance considerations. So really, what are we talking about here? We're talking about three areas. We have capital load analyzer. We'll go into more details of these, but just so you sort of know the scope of where we're starting out with compliance. And this is really a way to perform electrical load analysis. This is during normal operation and during emergency conditions. So it will help you show compliance to a number of regulations. Wire derating, so we can derate individual wires. We can derate bundles of wires. And we are trying to look for that sweet spot between let's not have wire smoke, let's not turn that wire into a fuse, but at the same time, let's save weight, and let's go to a smaller gauge wire where that's possible. And then 3D separation. I spoke about this earlier. How do we make sure that we have our signals separated appropriately? Things like primary and secondary or tertiary where aircraft have 3 sensors. And how do we not mix power and data and really comply with those early 1707 and 1709 EWIS regulations. And we're doing this for each flight phase. We know that companies have their own flight phases, and a lot of the analysis for a particular platform will follow the same number of, the same set and definitions of flight phases. So this allows companies to use their same flight phase system to do their electrical load analysis. So this matches all of their other documentation as well. So let's look more into that. This is my attempt to represent a fully populated electrical digital twin. So if you imagine that your aircraft or vehicle electrical system is all the way designed in Capital, you have everything in there, we can use that data and we can do some analysis on that data. You don't have to copy it, you don't have to dump it into Excel, you don't have to do anything with CSV files or input process something into Fortran. You can do it all in Capital. And so, for example, this is an AC bus. We have a few different loads connected to this bus. But if that's all in Capital, we can press a button and we can see the full load analysis. So here along the top, we can see our individual flight phases. We can see our 5-second, 5-minute, and continuous loading. And in this case, we have 3-phase power. So we can see all 3 of our phases here. I'll show you a demonstration in a couple slides so you'll get a little bit better feel of what this looks like. But it very, very much is a press of a button. So as you mature your design, as you iterate on things, you can very immediately see the impact of that design change to your electrical loading. And when I was in programs, the thing that mattered to me was not that your analysis, everything was always like 80% complete, right? It's almost done. What mattered to me is the report. When is the report going to get released? And a very nice thing here is this has a template-driven publication process. So users can input their template. You can make this look like all of your other documentation. It'll automatically insert your capital analysis results into your template. So you're always pulling from the most current, you're always pulling from recent data. You can, of course, add some other information, some other figures or diagrams or text to your report, and it will spit out a report for you. So here's an example of some of the figures and some of the analysis data that can be included in that report template for you. So now I have a brief video. So here's a single line diagram. For folks who have done this type of analysis, this should look familiar to you. In here we are selecting what we call a build list in Capital, and this is really where you can select your designs. I spoke about you can analyze all of your configurations. You do all of this through the build list. And here we click this button that goes to the ELA Data Manager. And here we can look at things like functional category. Edit Airplane is the screen from which you can define your flight phases. What we have here is the list from the MIL standard, but we know that people have their own flight phase definitions. You can add engineering notes because as an engineer, I liked adding notes, and we know that that's an important thing to be able to do. Here in the demonstration, you can see the user editing the functional category, which is a required element of the electrical load analysis report. And here we can do something really special. We can say that, hey, this equipment, this system is only active during these particular flight phases. So things like landing lights, for example, we would not expect to be powered during cruise. And so we can reflect that behavior here. We can do some advanced checking to make sure that we have power going to the correct systems during the different flight phases. And here's where we kind of went and explored the underlying design. So here we have a DC bus, view related items, and we can see that we have wing lights attached to this design. So this is all analyzing your primary data. Again, there's no copying and pasting. There's not a whole lot of manual work being done. And if we were to just click on the generator and click ELA analysis, now we can see the results of that electrical loading analysis. And this is what, for most companies, can take months on every configuration, every variant of that aircraft. You change a sensor on the aircraft and you have to go redo this analysis because you certify configurations, you don't certify equipment. So you need to make sure that equipment is valid to be part of that new configuration. And so, again, what was taking months, where we had people missing buses, we had them having quite significant errors, not necessarily analyzing the latest design, we can do all of this in Capital and see everything real time. So this is a very high level demo video, but hopefully will give you kind of a sense of what the tool can do. So we'll switch gears very briefly and we'll talk about wire derating. So we have followed the SAE guidance and MIL handbook guidance. And like I said at the beginning, we're looking at derating individual wires and bundles. And this follows the same principles as electrical load analysis in that if you have your electrical design in Capital, you have this electrical digital twin. Let's use this. Let's use that digital twin and really put that to work for us in the area of compliance. So this will analyze your design. It'll look at worst case current draw and it will derate for that. We know that temperature and altitude go into that equation, so most OEMs are using the service ceiling of their aircraft, but we can do a pretty sophisticated derating very literally at the press of a button. And so this is what that derating analysis looks like. And we can see some special things here. These cells are red for a reason. Right now these are 22 gauge wires and it's saying, hey, it should be at least an 18 gauge wire. So this is a very quick way to say, hey, I have a wire that may be a smoke condition. Let's change the wire gauge. And we have the same thing down below. We have wires that are 16 gauge. And this is saying, hey, based on derating, you can go to a smaller wire. So in this case, you can save weight. We saw, I'm not going to give you a quiz, but at the very beginning of this, we saw a statistic that said that the electrical system is now 3% of aircraft weight, which is very significant if you think about it. So every opportunity to reduce wire gauge is a big deal. We have our last example here, bundle capacity. This is saying this is overcapacity. So the engineer at this point would say, well, maybe I need to move some power wires into a different harness. So I don't have this overcapacity situation here with this wire bundle. So let's move on to separation. This is where I spent a lot of time as a systems engineer, was in the area of separation. So we can do things like, let's look at one harness, or let's look at many harnesses. So for example, you could select all of your harnesses connected to your inertial reference unit and see where that routing is. We know that when you have all of the harnesses displayed, it can look like a bit of a rat's nest. So this gives you the option to just look at some. We can look at individual wires. So I mentioned that this is a lot of my experience. I worked on a system for Cat 3 approach, Cat 3 landing credit, which for folks not familiar, it's when weather is really bad. It's where you can kind of mostly see the runway, kind of. So it's a very tight closed loop feedback control system. And when you're looking at control systems, particularly where you don't have a lot of margin to control the aircraft, latency is a very big deal, because a little bit of extra latency can phase shift that, and you can have a bad situation. So looking at individual signal routes for critical signals was a big deal for me. So I did this on paper and a highlighter, with paper and a highlighter. On a number of aircraft, on aircraft that you have probably all flown on, to try to see, are we taking the most expeditious routes for pitch angle, for example, because it is very important. So when I saw the capabilities in this area, I was really excited and really happy, because that would have saved months per program that I worked. We can also do things like measure distances. So for example, we have a primary and a secondary system. We can say, okay, out of this entire length of the aircraft, what is the closest that the routing for those two signals get? So a lot of applications there. I see this really being a very nice tool during certification audits. This graphical representation would be very convincing to a certification authority to say, hey, this is the closest that these two signals get, let me show you this data. I see that as being very powerful, because a lot of certification, yes, you have to provide the documentation, but another big element of that is kind of convincing them that you have a solid engineering and design process. And I think this could really go a long way to help around EWAS regulations. So this kind of brings us back to where we started. The model-based enterprise. It's the idea of a digital twin, and how do we really use that? How do we use that digitalization to sort of reduce the trade-off with complexity? We know all the good stuff that comes with more electrical content on an aircraft, but how do we use the digital twin to make it easier to show compliance to regulations or to industry guidance like SAE and MIL guidance? And we can do that, and capital's a big piece of that. So we were speaking today about this design space within capital. I just as easily could have had a very similar discussion around the other domains within capital to show the advantages that they can do. It's on the same lines, though. We have this data, we have it in a digital format. How do we use it? How do we validate earlier? How do we make verification easier? How do we make it easier to generate that evidence for compliance? So, some of the things we've spoken about, automate and manage. We can really use that digital twin to automate some of those design considerations for us. We can run design rule checks to make sure that we haven't violated some of the rules that we've codified for ourselves. We certainly can reduce program risk. Again, a lot of the compliance analysis is done at the very end of the program because you have hours to do it once. And so you wait until your designs are mature and then you do it. Well, that means that you're at the end of the program. And when you find problems there, the sky falls, right? Now you start pulling people from other program teams and you're kind of in quick fix-it mode. So we can really mitigate that. And then of course the iteration, we can use rules and constraints to design our systems properly from the very beginning and really enable program leaders to keep commitments. We have companies using this, using Capital all the time to help them meet it. We got feedback from a major OEM about 2 weeks ago that said for a new platform, all of their wire harnesses fit correctly the first time. That's almost unheard of. We know that a number of large air transport aircraft have had significant schedule delays due to they go to plug it in and the harness doesn't fit. So we have customers using Capital every day and using this idea of digitalization to validate earlier and verify. And that's what I have for you today.